Okay, today's easier than yesterday. We're going back to the AND case. What happens when you have multiple events that occur, one and another, or a string of events? More than just two would also work. The multiplication rule that we learned in chapter 13 was really simple. When you have an AND case, this happens and this happens. We always multiply. AND means to multiply. But the restriction in chapter 13 was events that were independent. We always had independent events when we first started. That's not always going to be the case. Sometimes after the first event occurs, the probability of the second event occurring is going to be different. And we have to adjust for that. So that brings us to a new multiplication rule, which is the general multiplication rule. General because it works even when things are independent, but it also works when things are not independent. So it works all the time. So we like the general one. The formal definition is a bunch of gobbledygook symbols. So let's see if we can't make some sense of it. The probability that A and B occur, so we want to think of this as an and sometimes we already know this probability. In terms of a Venn diagram, if we had a Venn diagram that had some overlapping events, some non-disjoint events, and we had an overlap or an intersection of two circles, and we know what percentage of outcomes falls in that intersection, then we would already know this number without having to do a computation. So really this formula is only when you don't already know that number and you have to compute it on your own. So we think of this as the AND case. Event A happens and event B happens. Both occur. So in the previous chapter we just said we're going to multiply the probability of A and the probability of B. We make an adjustment on this one because we start with the probability of A happening, just like before, and we're still going to multiply. AND means to multiply. The difference is anything that happens after the first event hinges on the fact that the first event happened, which means we have to see it as a conditional probability, the new probability of B, given that A has already happened. Now, this sounds really complicated, but in most circumstances, all this second piece requires is an adjustment in counts. We adjust what our counts are. And the most popular case is when we have cards to count. It'll make more sense when we actually apply it. So let's go ahead and go to the next slide so that we can see what it looks like in action. So when you move from just pulling one card out of a deck to pulling multiple cards out of the deck, you have to deal with the general multiplication rule if you don't put the cards back. So if you pull a card out of a deck and you don't return it to the deck and then you draw a new card, what's in the deck changes and you have to make an adjustment. The probabilities of what's coming out of the deck are going to change as you pull more cards out without replacing them. So you're dealt a 3-card hand, which means you're going to get a card, you're not going to put it back, you're going to get another card, not put it back, and then get a third card. So we are not replacing cards. 3-card hand, no replacement from a well-shuffled standard deck. So we need to do at least 7 riffle shuffles, is what we've learned earlier. What is the probability that they're all aces? Okay, we can count cards, so this is going to be as simple as getting our card counts right. Now in symbols, we want the probability of an ace, and another ace, and another ace. Now we can use an intersect command there if we want to, but the word and I think is a little more helpful. So an ace and another ace and another ace. You have to think of it as 3 distinctly separate events. Now the multiplication rule says we multiply when we have ands. And the probability of the ace on the second card and the third card are going to change because when you pull that first card out and you don't put it back, it changes how many aces are in the deck and therefore changes the probabilities. Let's deal just with the first ace. We're going to pull the first card out of the deck, get the first card dealt. We had a deck of 52, so 52 cards are available, total outcomes. Of those 52 outcomes, 4 were aces. So the probability of the first card being an ace is 4 out of 52. So that takes care of the first ace. And means to multiply, so we're going to multiply by what's the probability of the second ace. Well, we didn't put the first card back in, That means we now have 51 possible outcomes. Only 51 cards are left in the deck. Of those 51 cards, how many of them are aces? So we technically are doing a conditional probability here because now we're only looking at the 51 remaining cards. The probability of drawing an ace has changed. Of those 51 cards, since you already have one ace in your hand, there are only 3 cards left in the deck that are aces. So the probability of the second card being an ace is 3 out of 51. And another ace means multiply by the probability of a third ace. You didn't put the first 2 aces back in, so you now have 50 cards total to choose from, and of those 50 cards, exactly 2 of those are aces. So it's still a multiplication rule, but we've had to refine it to take into account the non-replacement of the cards, which changes probabilities. So the second and third probabilities here are conditional probabilities, but since we know how to count cards, we don't need a sophisticated formula to calculate those conditional probabilities. And from there, I would probably let a calculator do the work. If you want to be really clever, you could think of this as all one fraction and do 4 times 3 times 2, which is 24 on the numerator, and then divide by 52 times 51 times 50 as all one big fraction. Instead of multiplying 3 separate fractions together on your calculator, make one big fraction bar, multiply the top together, multiply the bottom together, all in one fell swoop. After you've done that, your calculator could do one of 2 things. This is a really small number, close to 0. So your calculator is either going to give you a string of zeros after the decimal, or it's going to give you scientific notation. So you could get an answer that looks like 0.000181, or it could give you scientific notation if you move your decimal over 1, 2, 3, 4 places. To the right of the 1, we would have a scientific notation of 1.81 times 10 to the -4th. On the AP exam, the readers don't care if you give them scientific notation or if you give them standard notation. Decimal notation works just fine, but if you give them the scientific, as long as it matches, as long as it's equivalent, it's just as good. So whatever the calculator hands you, jot it down and just move on. Be really careful because your calculator is going to give you that E notation, and you're going to have to watch for it. If you calculate a probability and you get an answer that looks like 1.81 and you write down 1.81 and don't catch the fact that there's a scientific notation, that there's a times 10 to a power at the end of that line of code, and forget to write that down and you report 1.81, that's not a good thing because we know that probabilities can't be bigger than 1. So watch for probabilities that look like they're bigger than 1. There's a scientific notation number there that you're going to have to deal with. Okay, let's do the next one. What is the probability that the third card is the first face card? All right, face cards are the cards that actually have faces on them. So those are jacks, queens, and kings. Things that have people's faces on them. Those are face cards. Aces are not face cards. Okay, so the third card is the first face card, which means the first card was not a face card. The second card was not a face card, but the third card was. So you still have to deal with 3 separate events. So probability of not a face card, and not a face card, and face card. That's your sequence of events. You got a not face card and multiply, not a face card and face card. So 3 separate probabilities must be computed and multiplied together. Alright, the first card, not a face card. Alright, there's 52 cards available. That's the easy part. Now, we got to figure out how many of those are not face cards. Well, each suit has 3 face cards, jack, queen, and king. So 3 face cards times 4 suits is 12 face cards. So if there are 12 face cards in the deck, 52 minus 12 is 40. There are 40 non-face cards in the deck. So 40 out of the 52 are not face cards. And means to multiply. We get a 3-card hand, which means we're not putting the cards back. So when we get the second card in our hand, we'll be choosing from 51 cards that are left in the deck We've already gotten a non-face card, which means now there's 39 non-face cards left to choose from. So the second one is a conditional probability hinging on what happened in the first event. And the third card is a face card. That probability, we have 50 cards left to choose from. All 12 face cards were still on the deck at that time, so there are 12 out of 50 face cards left. Okay, we'll let the calculator crunch some numbers. Again, I would suggest one big fraction bar, do 40 times 39 times 12 in the numerator, 52 times 51 times 50 in the denominator. It's going to be quicker than trying to simplify anything down. Just let the calculator do all the crunching. We're going to end up with a 0.141 as our final answer. You can write that as 14.1%, but there's no reason to. Decimal values work just fine. So, low chance of that happening. Only about a 14% chance. Alright, one more. What is the probability that at least one card is a diamond? Oh, at least one. That's the complicated stuff. If you do it, if you look at all the possible combinations, there's several of them. The first one could be a diamond and the second and third one not. The first one could not, the second one could be a diamond, third one could not. First two could not be diamonds, the third one could be. The first two could be diamonds, the third one not. The first and last one could be diamonds, the middle one not. The first one could be not a diamond, the second and third ones could be diamonds, or all three could be diamonds. So lots and lots of possibilities, and in order to take the approach of looking at all those possibilities, you'd have to compute all of those separate probabilities and add them together. It would be really easy to overlook a possible outcome. It would be really easy to use one more than one time. So the safer way for at least one is to learn the trick. And the trick is 1 minus the probability of the complement. We learned that before. The complement of at least one card being a diamond is that none of the cards are diamonds. So the quicker way to compute this would be 1 minus the probability that none are diamonds. None are diamonds means there's not a diamond on the first card, not a diamond on the second card, and not a diamond on the third card. So this is still going, this second piece here is still going to require 3 separate probabilities that are not independent being multiplied together. So the long way is to think of this as 1 minus probability of not a diamond, and not a diamond, and not a diamond. 3 not diamonds in a row, 3 probabilities multiplied together, and then we subtract it from 1. So we have to work on this second term of the calculation first. 1 minus, let's calculate some probabilities. Let's see, there are 13 cards in a deck that are diamonds, 52 total. 52 minus 13 is 39. So 39 out of 52 cards are not diamonds. So the first card being not a diamond has a probability of 39 over 52 occurring. We don't put it back in the deck. We're getting dealt a 3-card hand. So, and another not diamond is conditional, based that depends on what happened in the first card. Since the first card's not in the deck, we now have 51 cards to choose from. 38 of those are not diamonds. Then the third not diamond, multiply again. 50 cards are left. 37 of them are not diamonds. The calculator will handle this computation all in one fell swoop. 1 minus, make a fraction template, multiply on the top, multiply on the bottom, crunch all your numbers. I suggest that you try the number crunching, actually put it in the calculator, make sure you're getting the right answer to make sure that you're typing it in correctly. And you can check that. You should end up with a 0.586 when that computation is finished. All right, we have one more question today, one more example, and then we're off with homework again. So we'll finish this one up pretty quickly. So out of the card world, back to percentages. 32% of all team drivers fail the road test on the first attempt. So the probability of failing the road test on the first attempt is 32%. Okay, which means there's a 68% pass rate on the first try. Okay, so 32% fail, 68% pass on the first try. The percentage who pass improves to 85% on the second attempt. In other words, you only get a second attempt if you fail the first time. If you fail the first time, then the percentage you pass improves to 85%, from 68% to 85% on the second attempt. So the probability of passing on the first attempt and the probability of passing on the second attempt are not independent, because passing on the first try or failing on the first try changes the probability of the second try. The probability is not the same. What is the probability that a random team driver passes the road test on the second attempt? Which means we took the test and failed it, and we took the test again and passed. So that's probability of failing the first try and passing on the second try. A fail, then a pass. Okay, well, what's the probability of failing on the first try? 32%, so 0.32. So we're going to use decimals this time. And means to multiply, so multiply that by the probability of passing on the second attempt. Now, probability of passing is 68 on the first attempt, but it increases to 85 on the second attempt. That's the conditional probability. If we fail the first time, then the probability changes to 85% on the second time. So passing the second time is an 85% chance, and means to multiply. Multiply your two numbers together. It's super simple, and you get 0.272. So you have a 27.2% chance of a fail, then a pass. All right, that's it for today. Your day for homework is in your notes. Spend the rest of the time working on that. Work together, check your answers, talk things out, and we will finish this chapter in tomorrow's notes.